I'm Tom Ryerson. I'm a part of the proposing team. Steve Wassie is the PI of this NASA Earth Venture Suborbital 2 mission that takes that aircraft, the world's largest chemically instrumented research platform, around the world 4 times to try to get some in situ data that are needed to constrain these global scale chemistry, climate, and chemistry transport models we rely on to make intelligent decisions about our atmosphere. So very briefly in the overview, the motivation for the ATOM project was that CCMs, chemistry climate models especially, really embody the state of our knowledge of atmospheric choices we can make. And yet they really struggle in the present day to reproduce basic atmospheric observables. The 3 examples I'm showing here are for methane lifetime, which we know quite well to be about 9 years in the atmosphere. The range of high quality CCMs we have right now vary about that correct number by a factor of nearly 2, from 7 to 14 years. And that has implications for what we do about methane and other things that are lost by OH in the atmosphere. The middle example, ozone trends, the surface data for some high altitude European mountaintop sites, these longer term ozone data records are very poorly predicted by a suite of models that have been examined, including the CCMI models you may have heard of. There's one example from NOAA GFDL there. They really fail to predict ozone maxima, season, latitudinal distribution, and many other aspects of ozone. And that really affects our ability in IPCC to accurately give a value and an uncertainty on the radiative forcing from tropospheric ozone. And then finally, on the right-hand side, I'm showing altitude versus black carbon aerosol on the left-hand panel and organic aerosol on the right-hand panel. The black data are observations from a previous airborne project called HIPPO that show on that log scale a systematic overprediction from models in black carbon and its radiative forcing at high altitudes in the Pacific. That's a giant change, and the models are struggling to assimilate and better simulate the observations. The organic aerosol panel on the right shows the same AeroCom suite of aerosol models span a factor of nearly 200, and prior to ATOM had 0 data to constrain them really. So they really fail in terms of getting sources and or sinks or both for aerosols correct at all. The data really were lacking prior to ATOM and perhaps HIPPO to even vet or discriminate between these models. So that was the motivation. On the next slide, you can see in another example, those 8 panels on the left, those are 8 different global scale models showing a slice from surface and pressure to about 200 millibar, which is about 12 kilometers, from the South Pole through the equator to the North Pole for formaldehyde. They look quite different, and not all of them can be right in this slice. They really diverge, and there was no way to constrain one or another from each other. So to that end, we proposed and were successful in getting ATOM funded by NASA. It's a 5-year project now to generate the systematic observations through the remote atmosphere to really quantify the current chemical state of the remote troposphere and lower stratosphere. So we wanted to capture the way the world really is right now with a breadth of measurements from gas phase species to aerosol composition and microphysics, radiation and meteorology. And so some of the initial observations of formaldehyde in the same presentation as those 8 model panels to the left, we're showing the ATOM, the first circuit around the world, showing on the same color scale that the observations really belie most of those model simulations. There's much more formaldehyde than we can currently account for in models, and we're struggling to understand what its sources are and why it's there in such abundance across such a wide latitude range in both the Pacific, which is shown here for August, and the Atlantic as well. So to provide these global scale observations, that cartoon on the right shows you how we're exercising this in situ chemical payload on the DC-8. We're taking it from the surface of the ocean, nearly 200 meters, to its ceiling at 14 kilometers, doing these continuous up and down vertical profiles from Arctic to Antarctic in the Pacific and then the Atlantic Oceans, 4 times, once in each season in the last couple years. We're going to launch our last circuit of the globe in about a month or so. And so this is the way we get a tomographic slice, hence the name, of the middle of nowhere in the Atlantic and Pacific to evaluate the simulations and hopefully measuring enough things simultaneously to identify precisely where they are imperfect so as to improve them. And I think on the last slide, just quickly in the overview sense, we're measuring many, many different things simultaneously on the NASA DC-8 with very high spatial resolution. So we're providing a lot of new pieces in a systematic sort of chemically agnostic sampling approach to the puzzle of the remote atmosphere. So adding pieces doesn't necessarily make you a picture yet. We're still just beginning the analysis. You'll hear some of that from the other 3 speakers queued up today. That's all I have for the overview, and I'm happy to take any questions. And unshare my screen.
Tom, I just wanted to add that the ATOM-1 and ATOM-2 data sets are publicly available.
That is correct. ATOM-3 will be in July, I think.
Yeah.
And ATOM-4, maybe 6 months after that.
So it's once the data is finalized, all the QA, QC, and calibrations are applied, then the data becomes public. So NASA's very proud that the data goes public so quickly. We want to collaborate with the community. We want people to use the data and just, of course, acknowledge the PI who collected the data and perhaps consider including them as a co-author if, or certainly sharing the paper with them in advance so they can hopefully give you some helpful feedback.
Right, thanks, Barry.
Oh, and there's a DOI for ATOM.
Of course there is.
A digital object identifier. And so if you do use the data, please include the DOI, and that way whoever reads the paper can click the link and instantly find all the data. So, all right, so Meredith, who's next on our schedule for the ATOM team? I don't have it in front of me.
I think that's me.
Oh, thank you.
And I did it kind of arbitrarily, so if that makes sense. Okay.
That'll be fine.
Unless Jack wants to go first for more context, I don't mind.
No. You're all.
Okay, I'll do share screen, and at the moment Jack is looking at us.
We can see it now.
So you can see some pretty pictures?
Yes.
Okay, so to reiterate Barry's point, all the data is available. If you Google espoarchive.nasa.gov, you'll find all of the data that's publicly accessible. ATOM-3 will be available this summer. So I'm just going to give a bit of a context on some of the processes we're looking at. Jack is going to look at this in a much bigger context and look at kind of the more longer term. I'm just going to pick a couple of things that we've seen as we've gone through the data. Pretty short and sweet. A lot of it is still in development, but if you have questions, please let me know. So this is just the ATOM 1, 2, and 3 route that we took. What you can see in the Arctic, let's see if I have a mouse here. Apparently I do not. Can anyone see my mouse? No, never mind. So we followed the same route pretty much down the Pacific. So leaving from Anchorage, we head for Kona, Hawaii. But on the way back up, we've had 3 different routes over the different ATOMs, depending on conditions, places we could land, runways that were usable, this kind of thing. And some of that will have an effect, but we generally got as far north on all 3 of the ATOMs as we could. For ATOM 4, the plan is to fly into Thule, which is the blue dot towards the top of Greenland, and over to Alaska from there. So I work a lot on looking at CO2 and methane from Arctic ecosystems and work a lot on permafrost. So I was giving a couple of slides at the NASA Above meeting last month. So I pulled together just a map of where the permafrost regions are. And we've covered quite a lot of the area around that on the western side, or what exactly does west mean that far north, but on the North American side. And this shows the 3 different, the extent of each one, and the contrasting color is where we go below about 1,000 meters. So it gives you an idea of how many profiles we managed to get in the Arctic. The red is August 2016, the blue is February of 2017, the green is October of 2017, and then we'll be doing similar route as the green one, hopefully, or the blue one actually, in May of 2018. So some of the things that have kind of come up as discussion points, include looking at methane enhancements over the sea ice in both August and October of 2017. And that's something that has been seen in HIPPO and on the NOAA Alaska Coast Guard flights. But we haven't had enough chemistry to know what's actually driving that. It's a big research question of what exactly could be producing methane over sea ice when it's broken sea ice, the regional extent of that, and we're going to do some work with the different groups that have been measuring in the Arctic, looking at those fluxes to see if we can quantify the fluxes and figure out what the drivers are. And there's a group in Sweden that were actually measuring at the other side of the Arctic on a ship in August 2016 who are also seeing similar types of behavior. So that's going to be quite interesting. For the methane and CO2 enhancements in October 2017, we're seeing numbers that are fairly consistent with the NASA above Arctic cap flights, which Colm Sweeney is leading out of ESRL also. And I think that would be quite interesting to see, given Ascends from NASA was flying up there over the summer. And then we're tying in with the Arctic cap flights, how that will look. During ATOM 3, we also saw a narrow pollution plume, if you want to call it that, which seemed to be more like a gas flare, that we saw that kind of behavior as in a very narrow plume. And the question is there a new development in the Arctic? Is that going to change these kind of behaviors as we go forward in time? So there's new LNG plants that have been commissioned within the Arctic Circle. How is that going to affect our overall pollution? And something we've dug into a little bit more here is biomass burning in Arctic boreal regions. So that's kind of what I'm going to come on to today. But if you have questions at the end about any of those other things, please just let me know. So Sarah Strode has just submitted a paper to ACPD looking at the GEOS FP, which is the GEOS 5 forward processing. It's the reanalysis of the GEOS 5 that we often use as our predictor to help in flight planning. We don't change our flight plans to match it, but it gives us an idea of interesting science we might see along the way. And when she bins all of the data, one thing that comes up is how under-predicted the CO is in the Arctic. And this is from 60 degrees north, roughly, and in the Pacific and the Atlantic, from both different types of inputs that are just missing. So if we look at the flight plans on the left, we have the ATOM 1 Anchorage to Kona. So this is leaving Anchorage. As soon as we leave Anchorage, we see this pretty high 300 ppb of CO, and it's not captured in the model at all. There's a very slight amount of about 10 ppb that it thinks could be global biomass burning, but it doesn't attribute it to Eurasian biomass burning. And it seems to be not captured at all in the Pacific. In the Atlantic, we have, I'm struggling to see it myself because you're all staring at me instead. On the right-hand side, we have the Azores to Kangerlussuaq. So we go as far north as we could over Greenland and then land in Western Greenland. And what we see is that there is some amount of biomass burning captured by the model, but it's way underestimated. So the question I've been trying to kind of tease out is why that is. And this is some work that Katie Travis and Colette Heald have been doing at MIT, and they've been looking at the different fire emissions databases that you could use to drive the CO. And for both of these, if I go back one slide, this is all for CO. We also have input for black carbon, for all the different chemistry. It's just I'm measuring CO, so that's what I'm interested in looking at. So from the fires, the GEOS 5 FP uses QFED. It uses the MODIS fire count with a rough emission inventory to say, okay, this is how much CO should be in the atmosphere at that time. But the GEOS Chem, which is a GEOS 5 driven WINS, but a full chemistry model, driven by either QFED, which is the quick fire emissions database, the GFED, which is a reanalysis product, or FIN, which is a completely independent fire emission database, doesn't capture the high altitude fire type behavior that we're seeing in the Arctic. So if I look at all the other chemistry, what we're seeing between north of 50 degrees is all fires. And yet all the models seem to be missing that. And I've been kind of wondering why. So I looked briefly at the GFED 4 and the QFED. So QFED, which is the quick product, is not capturing half of what GFED is predicting for both Siberia and for Northern Canada. But I also went back to the MODIS product and looked at the MOPPET day-to-day CO, the total column CO, for most of July and into August of 2016, it's clouds. There's one small plume of CO captured by Moppet. The rest of the month is all just cloud covered. So it could be that we're just missing the entire input for all of this. So that has me wondering about how well does Moppet reproduce the massive fires that either create their own cloud systems that we just can't see through, or is it just that they're cloudy and so far north they just never capture them? And that's something that we've kind of started discussing in-house here. So when I was at the above meeting, we chatted a lot about like the impact of biomass burning and fire. The fire disturbance working group has been doing a lot of work on that as part of above. And Brendan Rogers pointed out that I should be looking at the small fires, GFED4S, which tells you where the smaller fires are and actually gives you much more, I guess, a better resolution of where the fires might be. So I think that could be quite interesting to see. I mean, you can see from Siberia, we have a couple of small but intense fires on kind of Kamchatka, Eastern Siberian region. How much of an impact do they have? So we're going to have a look at that and see, do we get a better relationship with the GFED4S? But then again, this is an after the fact product. If it's cloudy, it knows when it was not burned and it can tell you when it's burned, but it has no idea when the emissions were in between. So the longer the cloud goes on, the less resolution we have on that. Then just a quick overlook at ATOM3, which Barry said was okay because there's no numbers. This was leaving Maine, heading to 80 degrees north and landing in Anchorage. So as we left Maine, we had this really strong jet. And then we passed north of that, looking at the different things. So on the top left side, we have the wind speed, and you can see where the jet is, and then the winds drop way down. And then this is looking at different gases that we see as we go along. So the ozone, we're seeing stratospheric influence, and then we also see about 5 kilometers, this slight decrease in the ozone. That's actually at the same place as where we get the chloroform increase, methane increase, CO2 increase. It's looking like a big pollution plume from Asia or from that general region. And that's something that we're going to have to look into. We've seen this on a few different ATOMs. So how much of an impact does that have overall? And then I think Jack is going to start talking about the longer term context of some measurements like this. So that's me done. I was a bit quick, sorry.
No, that's fine. This just leaves more time for questions at the end.
Are we taking any questions now, anyone, or are we moving on?
We have time for questions.
Shall I steal the screen and try to find my presentation?
Sure.
Or do you want to go back and show any slides again?
Oh, I just hit the unshare screen, so I can grab it back again if I need it.
Well, is there any questions, anybody?
That means no. I think I spoke too quickly and nobody understood a word I said.
Hey, Roisin, this is Chuck.
Yeah.
With that, those pollution events that you were seeing going across the Canadian archipelago, is there any aerosol loading associated with that? I haven't looked at that case yet.
Yeah, I'm going to have to dig back into it. There was a lot of sulfur at the time, which had me thinking it was some sort of, something had burned. And then I got chatting to various people, and it's about the time that the LNG plant on the Yamal Peninsula was commissioned. So I think if we do a bit of digging around, we might be able to see what exactly is driving it too. But it was a very narrow plume. I think I remember at the time that there was some aerosol in it, but what else is there, I don't know. Most people are just getting to the stage of submitting data now. So it'll be
okay, yeah, black carbon might be very informative as to the source.
Yeah. And my question is, if as development progresses in the Arctic, how much more are we going to see of that?
I was interested in how different the fire emission inventories are.
Especially in the Arctic.
Yeah, and if you're relying on satellites and it's cloudy all the time, so.
Well,
Yeah.
it's not just an Arctic issue, Roisin. I mean, we get the same under prediction for African and South American and I think even Indonesian biomass burning in different parts of the world from the observations. So it's it's hard to say whether it's a source problem or just not enough fires going into the model problem. A source in terms of emissions ratios.
Well, we know something about the inventories, and the ones that are based on satellite observations miss small fires systematically. It's not just a matter of cloudiness, although that's a factor too. But again, I think somebody mentioned GFED 4.1S, that includes some of the small fires, some of the agricultural and shrubland fires that are generally missed in the hot spots that we get from MODIS. And that tends to help in a lot of places.
Thanks, Ralph. All right. If you have questions, save them for the end. We'll have plenty of time at the end. So go ahead, Jack.
So is my screen showing?
Yes.
Picture of Alaska out the window of the DC-8. So there's a lot of people that talk about this at the ATOM science team meeting. In the end, I'm focusing today only on short-lived climate forces, which turns out to not be data from any of the people named here, but so I'm relying on a lot of other people from the ATOM science team for the data. And also, as this slide points out, I was very interested in comparing some of what we've seen on ATOM 1 and ATOM 2 to earlier measurements by NASA's ARCTAS campaign in 2008, and then before that in 2000, the NCAR TOPSY campaign. And then AMAP has done a lot of recent assessments. So I look for some long-term and seasonal trends from ground-based networks in the Arctic from these two AMAP reports. So we've seen a version of this. These are the flights we made into the Arctic in ATOM 1 and ATOM 2, as Tom and Rogine both explained. So in the beginning of each of these campaigns, we go up to Alaska and fly over the Arctic Ocean near there. On ATOM 1, we went to Greenland and then back over the middle of the US. ATOM 2, we made the transit back to Anchorage, and ATOM 3, we also traveled on the way back to California through the Arctic, and we hope to do the same on ATOM 4. So these are the flights that I'm going to focus on. I'm going to show plots that show vertical profiles of bins of 1 kilometer from all 5 of these ATOM 1 and ATOM 2 flights. And I'm going to compare them to the earlier results from ARCTAS. These are all the DC-8 flights during ARCTAS. There was 2 phases. In April, we were based in Fairbanks and flew all these flights that you can see for the April rendition, including some over to Greenland. And this line, if you can see my mouse, I will divide the ARCTAS data into Eastern and Western Arctic in some of the later plots, mostly because when we look at TOPSY, it was exclusively in the Eastern Arctic. TOPSY was a kind of unique campaign. We did 7 different trips, about 2.5 weeks apart, starting in Denver and going up to Churchill and then up to Thule, and maybe on good trips, about half the trips, we were able to fly out over the sea ice north of Alert. And then just for reference, I think everybody on the phone should probably know many of these places, but here's just locations where there are ground-based stations that have been measuring methane for a long time. Some of them have also been measuring ozone, black carbon, and sulfate aerosol. So there will be plots later on, certainly, that look at records from Alert, Summit, Pallas, and Barrow. So just so everybody has an idea where these places are. We also fly over Cold Bay on all the ATOM missions. Cold Bay falls out of my definition of the Arctic. Everything I'm going to show you is north of 60. That's kind of an arbitrary selection, but that's just the one that I made. So I want to look and see if these short-lived climate forces, and my plots are all going to show the same kind of a format. So let's just look at this. So it's 1 kilometer bins, averages plotted here, trying to color code it to show the seasonal progression. So for ATOM 1, we're actually talking about August, right? So it's a warmer color. ATOM 2 is in February, so it's cold. We go back to TOPSY, we flew from February all the way into May, getting into the springtime, the greenish colors, and then getting warmer as we move towards summer. And then in ARCTAS, most of the flights that were in the high Arctic were during the April campaign, but we did make a couple of trips in June. So obviously we see a pretty striking increase in the mean concentrations of methane over this time period. Also a pretty strong seasonality where we have peaks in the cold months and it drops off in the summertime. This is really apparent at the at the surface more than in the mid-troposphere. I'm not sure I understand that because it definitely looks like a kind of a global signal of methane. There are obviously events that, like Rogine was showing, but in the average, we're not seeing a lot of methane coming out of the surface Arctic just yet that's driving the distribution here. And so then just to put this in the context of a long-term record, this is from a number of stations in the NOAA FLASH network where they believe that these are background stations that are rarely seeing local signatures like seasonal releases from wetlands or flaring or any kind of petrochemical kind of activity. And you can see this upward trend. I don't know, I got this video in the middle of my plot, but so you can see that I'm just saying that in Topsy, our surface levels during Topsy were about 840 ppb in the mean, and that's pretty close to what the network was saying. Arct has the same. Seems like there's been another rapid increase in methane concentration in the Arctic. Notice that this plot stops at 2014, and we're talking about 2016 and 2017 for ATOM. I don't know if it comes up all as high as what we're saying here, but it's a pretty striking trend. Another climate forcer that we have interest in is ozone. Short-lived climate forcer is also kind of interesting chemically in the Arctic. If you look again at these same plots comparing all these missions, just looking from a distance at the plot, it certainly seems like ATOM has got less ozone than either of the two earlier missions. But I think that's really a function of seasonality, because if we look here, these elevated levels of ozone in the mid-troposphere in both ARCTAS and Topsy are in April and May. And we're looking here at ATOM at seasonality of February and August. So we haven't sampled in the spring. I think we may, prediction, see something more like this when we go there on the next trip. And of course, we're all interested, most of us on the call, in these ozone depletion events and halogen chemistry. You can see that showing up in the lowest levels in certainly Topsy, to a lesser extent in the later two missions. But we've been speculating whether we're going to see any of that in May or whether we're going to be too late. But so if this is just seasonality, then I don't see a strong signal for a major trend over time over these 18 years. Here's a plot again from NOAA. These are surface monitors. They're not FLASH, but there's one at Summit that's been operating for about 10 years and one at Barrow for much longer. We can see a seasonal pattern here where April, May is highest at 3 kilometers in the free troposphere at Summit. A suppressed seasonality at Barrow, maybe partly due to these ODEs, but maybe also the dynamics. And forget about all these colored lines here, except it reinforces a point that we've heard made already, that the models don't necessarily do a great job with simulating any of these things. And that was the point of the AMAP paper that I stole this plot from. And then finally, just to look at that longer term trend that I say, I don't see it in the airplane stuff. If you look at the full record from Barrow for 30 years, there's a very small increase maybe. If you start in 1970, you go all the way to 2010, so 40 years. But certainly over the last 15 years, it doesn't seem like much is changing. So it's relatively consistent with what I speculated from the airplane stuff. Black carbon is one, of course, that we're very interested in. The community has a short-lived climate forcer that maybe we could buy some time for the polar bears if we reduce black carbon reaching the Arctic and melting all the snow and sea ice. Well, in this plot, it looks like the Arctic is way cleaner during the ATOM years than it was during ARCTAS. And that may be correct, but it's also very much driven by the fact that in the April campaign, certainly the Western Arctic was heavily influenced by biomass burning emissions from Kazakhstan and other parts of Russia. And so you can see that there's a really enhanced BC during the ARCTAS time period that we just haven't seen to the same extent during ATOM. And I think that's about all I want to say about that. However, there is an indication, that we should expect a pretty strong seasonality in the concentration of black carbon at the surface related to the well-known Arctic haze phenomenon. And here's a number of stations in the Arctic where now we want to just look at the dotted line and the gray bar, which are the observations, and kind of forget about the models. But you can see that there's a peak that is in the winter and it kind of dies off into the summer across all of these stations. Maybe we see a little bit of that in the airborne data, but it's not so convincing. And then over the longer term, these stations are showing a really dramatic decrease in black carbon. And so what these plots are showing is the annual trend over the length of the record, the trend during the wintertime Arctic haze season, and then the trend during the summer. And so they're saying that the trend in the summer is not significant, but certainly a downward trend in the annual and the Arctic haze season may be a hint of an increase in recent summers of Barrow that could be related to more biomass burning or increased industrial activity. I don't know. On the right is a comparison of previous measurements from aircraft that go way back to the A-gas years. And this might not be the simplest comparison to make because there's many different techniques of making the measurement in here. But these show a dramatic decrease in black carbon from the early to mid 80s until recent stuff, including HIPPO. And our numbers from HIPPO and ATOM, I mean, these are all from Shuka Schwartz, are all quite comparable. So maybe the Arctic is cleaning up in black carbon. Although Barrow says maybe in the summer we're seeing a little upward tick. And so something to bear watching. But I think this relatively large decrease over the last 20, 30 years is consistent with a lot of other evidence, and so that maybe black carbon is not going to be the easy salvation that we hope, because it already has dropped from recent highs. And then one last spot is another climate force that I don't really want to emphasize too much, but sulfate is another pollutant that's actually counteracting all those other gases that and black carbon we just looked at are warming. So sulfate could be cooling. Although the Arctic is pretty touchy, you have to have a very, very bright aerosol to actually do cooling. And it certainly is up there in abundance to impact clouds, and I think that's a bigger uncertainty. So sulfate has a very pronounced seasonality, as reflected in the Topsy campaign, where as you go into the season, you see this Arctic haze build up and then deepen and deepen. And we saw that a little bit in ArcTest as well. And April looks very much like in the Eastern Arctic, looks very similar between Topsy and ArcTest, no big change. We have not seen the springtime peak in sulfate yet during ATOM, but hopefully we will on the next trip. And I think I have just one more slide, which is just the conclusions. I think that the aircraft stuff is good because it may allow you, if you look at the level of detail that like Rosine was talking about, to understand what may be driving plumes. But right now it's reassuring that the trends are largely compatible with what we're seeing at the surface sites. So that's all I have.
Thank you, Jack.
Jack, this is Chuck. I have a quick question for you.
Go ahead, Chuck.
So your slide that showed the seasonal cycle of black carbon at the surface sites, I think it's 3 back.
Yep.
I was looking at 2008. Yeah, that one there. 2008, yeah. Which was the year with all the biomass burning in Kazakhstan and Russia.
Right.
It doesn't really stand out there. Is it any different than any other year in the Barrow record, for example?
No, I mean, it's a little higher than 9 or 10, but you're right. It's not as high as some of the earlier decades, right?
Right.
I mean, 2000, I think, is the highest one in the last 10 years, but not in the entire record by any stretch.
Right. I just wonder if that's indicative that maybe these biomass burning episodes are pretty common.
Well, I guess I read this paper by some Chuck Brock character who said the black carbon that we were all excited about during ArcPAP and ArcTest never mixed down to the surface, so they wouldn't have seen it at Barrow.
Yeah, that's right. So, I mean, I guess one of the questions is how representative are these surface measurements of what's going on throughout the tropospheric column?
Yeah, and that's a question is, what do you think about the ones on the right there from the old AGAS stuff? I don't know. I think that the ATOM stuff may be showing that there's the surface down to 1,500 feet is pretty similar to what it is in the bottom 2 or 3 kilometers. Right, our measurements during ATOM is not showing any real big gradient. But if you look at the ArcTest stuff, the stuff at 3 and 4 kilometers, 5 kilometers, 6 kilometers is way higher than what we measured at 500 feet.
Mm-hmm.
So it's always.
Sorry, go ahead, Jack.
No, go ahead. I agree. It's always a good question: is how does a surface observation relate to what's higher up?
Right. Well, I was just going to add that the horizontal dimension to this, which is that in the satellite data, you know, we do see some pretty large gradients in places, and having such a stably stratified atmosphere that you have in the Arctic, mixing isn't what we're used to thinking about in mid-latitudes. And so sometimes it may not just be the vertical distribution that's not uniform, but you know, we assume that transported constituents would be well mixed horizontally, and that may not be applicable either at these high latitudes, just based on the stuff we've seen in the satellite data.
So what satellite data do you think is really doing a good job so far north, Ralph?
Well, nobody's doing a really good job, but if you take together the Calypso data, which is probably the best data, and you know what we can do with MODIS and MISER, which is not ideal by any means, we just get that impression just from where we can do retrievals for various reasons. I mean, sometimes it's situations where we're over water that doesn't have ice on it, for example, and it doesn't happen to be cloudy, and we can do a retrieval. But we do see gradients, and
right.
They don't look like mid-latitude kinds of things where transported aerosol tends to be, you know, sort of spread out pretty uniformly or fairly uniformly over a fairly large area. It looks different, and the mixing processes, it doesn't surprise me that the mixing processes would be different because of the stable stratification of the atmosphere.
No, it was a good point, and you know, you may have seen the paper that Jenny Thomas just published last year that I was part of, with trying to link the satellite products, you know, making a connection between fires in Greenland. And it was a challenge trying to watch those. You can see it, right? Occasionally you get really good images of the smoke plumes, but then they, you know, something happens with a cloud or whatever. But I agree that Calypso has been a big help. Someone else was asking a question. I'm sorry, I stepped on you.
Hi, this is Arina. Can
go ahead,
you hear
Arina?
Me?
Yes.
Yeah, hi. So I agree with you that the fact that we don't see all of the stuff from the pre-troposphere mixing in the boundary layer, but sometimes we do see it, and I don't know how often that needs to be looked at. We've been looking at the aerosol measurements at the different, you know, wavelength spectrum from the GMD group at the surface in Barrow, and you can actually see that the particles that are associated with the fires getting into the boundary layer mixing up. I'm not talking about black carbon specifically, but that was the aerosol measurements that we've looked. And I also agree that trying to use the satellite or reanalysis information to confirm what's happening at the surface, yes, it is extremely difficult. So we've tried to correlate with the aerosol product from NASA, and it's not always, you know, vertically correct for the surface. So we need probably a little bit more measurements. I don't know if it's possible to do more of the aerosol measurements on the aircraft, go up and down, and trying to identify when the mixing actually is more happening than not. There are some measurements from the our program or DOE program in Barrow that measure the boundary layer. So that's probably another thing to look at and see how well that mixing occurring. So summertime versus wintertime, and I think it's different.
So just one comment about using the satellite data. The standard products from instruments like MISER and MODIS are not optimized for Arctic conditions. So I mention that only because, at least in principle, it's possible to get more out of some of that data by using research algorithms rather than the standard operational algorithms. that may be less true for Calypso, but it's definitely true for Miser and Modus.
Very good point. So you're saying anybody wants to get the best Miser product to give you a call? Is that the word?
Well, the problem with the research algorithm is that you have to take every pixel with a tweezer and work it through. And so there are severe limitations on how far we can go with that. We do case studies, and headquarters has been encouraging us to try and streamline and automate some of that process. And we've been working toward that, but it's not at all simple to do. What we've been able to do is show what the capabilities are under reasonably good observing conditions with a research algorithm. We've been able to show that, and we've published that in various places. But to actually generate lots of product, we're not equipped for that at this point. Hopefully we'll get there one of these years.
Wasn't there something about a golden day over the central U.S. in 2014? Or is that 13? I forget. Lots of smoke from far away.
Oh yes, we have
your
golden
point is well
days.
taken.
Yeah, we have golden days. Sorry, go ahead.
That happens every year, Jack.
We're very useful then.
All right, we might want to move on and give Chuck a chance. Go ahead, Chuck.
Okay, so Jack, you need to give up your screen.
Stop sharing.
Okay, Chuck, we see your screen. And now yep, that's working. Go ahead.
Okay, so I'm going to change gears a little bit and talk not about current and past projects like ATOM, but to talk about a potential future project called Impact. And the goal of this is to get better understanding of Arctic pollution by studying mid-latitude processes, paradoxically. So the reason that we're particularly concerned about pollution in the Arctic is because Arctic climate is affected by this pollution through its interaction with sunlight directly, the effects of the pollution on clouds, and changes to snow brightness, although that's probably a very minor effect overall in the aerosol, in the Arctic radiative budget. But we're also interested, not my own line of research, but others are interested in how toxic compounds can be carried to the Arctic and deposited on the surface, get incorporated into Arctic ecosystems where they bioaccumulate and affect those ecosystems. So what I want to point out is that pollution in the Arctic doesn't just come from northern sources like Europe and Russia, but there's also a very significant component from mid-latitude sources, including North America, the US, and East Asia. So global models are, even if they have the same emissions, often give us very wide diversity of abundances of these sort of climate forcing pollutants at high latitudes. And what I'm showing here is a set of model runs. Each line of a different color is a different model. There are 11 of them here. Some are chemical transport models, some are chemistry climate models. They've all been initialized with the same emissions inventory. And on the left is black carbon in March, and on the right is sulfate in March. And this is from 50 degrees south up to 90 degrees north. And so you can see that in the southern hemisphere up into the lower mid-latitudes, the models are in pretty decent agreement in terms of the total column abundance. But then once you get north of 30 or 40 degrees, it all falls apart. And there's this incredibly wide discrepancy in black carbon in the column burden of the Arctic. Now, these models agree a lot better with surface measurements, which might suggest that they've been adjusted to try to do a good job of matching the surface observations. In terms of integrated column abundance, there's a lot of diversity. And it's true not just for black carbon, it's also true for sulfate, and there's an even wider diversity of model results. And it's pretty interesting and really suggests that there's a problem here because these models are really essential to understanding our current atmospheric chemistry, predicting the future composition and climate, and to developing mitigation strategies. So we really need to narrow down why these models are in disagreement with each other and figure out which ones are right and ensure that we know that they're right. So this begs the question, why do models diverge at high latitudes? And the simple answer is that they really just don't simulate the transport or removal of pollutants in weather systems that precipitate very well. And this has been shown in that Eckhart et al. Paper, but in several other ones as well, where they really focus in on this transport in cloud systems as being the main cause of model disagreements with each other and with measurements. So of course, pollutants are emitted near the surface, and to get to the Arctic from mid-latitudes, they have to be lifted up to higher altitudes. And this lifting occurs usually associated with mid-latitude weather systems. It can also be associated with deep convection, big thunderstorms, but those are most prevalent at lower latitudes or in summer. So in the springtime, when the pollution is at a maximum in the Arctic, it's really these mid-latitude weather systems that are transporting the bulk of the pollution to the higher altitudes in the Arctic. And as this lifting occurs, clouds form, rain forms, a lot of the pollutants get washed out, some don't. The remaining pollution is carried at high altitude to the Arctic, and it continues to evolve during this transport. So we really need to understand this process here from emission through this wet removal process in mid-latitude weather systems to understand the Arctic. So where do these weather systems form? That's where we want to go to study these problems. And the answer is downwind of North America over here, and downwind of Eastern Asia here. Happens in the Southern Hemisphere as well. Of course, that doesn't affect the Arctic. So these are based on reanalysis trajectories showing where lifting occurs from the boundary layer to the free troposphere. And these locations of these warm conveyor belts and weather systems are just downwind of the major pollution sources from North America over here and from East Asia over here. Notice that there's not a warm conveyor belt system or weather system downwind of Europe, Northern Europe, but that is further north and is actually entrained into the Arctic directly. When the Arctic air mass passes over these sources, it picks, like it is this week, like right now, it picks up these pollutants and carries them back into the Arctic when it retreats. And that provides the surface pollution that we see at the ground sites in the Arctic. And then these sources are what are affecting the Arctic pollution at higher altitudes. Now this is an average from, I think, I can't read behind the pictures, but I think it's 2005 to 2014 average. And what's really happening is, oops, the back one, is that these emissions are changing with time. And this is NOx emissions in the US on the left panel and SO2 on the right. And then the same emissions from China on the bottom two panels. You can see that NOx emissions in the US have gone down through 2010 and they continued to fall dramatically. And so has SO2. And we're now at a very low emission rate in the Eastern US. China has gone up and then it's basically leveled off in the past 2 or 3 years and maybe beginning to decline in terms of SO2 emissions. All these different lines are different emissions inventories. You can see there's a pretty wide diversity in emissions estimates from China, but they're all showing generally the same trends. Okay, so to really improve the model simulations of Arctic air pollution, we paradoxically need to go study pollutant removal and weather systems downwind of China. And so that's the basis of this proposal called IMPACT, which is investigation of multi-scale processes affecting atmospheric chemical transport. It's a proposal I'm working on with Tom Ryerson and Jack and 3 others. It's going to be submitted in April. The idea is to take the NASA DC-8, the same platform that flew on the ATOM project, with a very similar payload, and to fly it in spring 2021 and 2022 out of Japan, and fly it over the Pacific. And we would make measurements in this region where there's a lot of uplift in these warm conveyor belts with cyclonic weather systems. We'd measure in the outflow coming out of these weather systems. And if the opportunity permits, we would probably follow a couple of these systems downwind toward where they enter the Arctic or head down to North America and study the processes occurring. We would really focus on measurements to evaluate the models and focus on determining the causes of model bias and diversity. And ideally, if this is funded, we would hope to entrain other aircraft, surface measurements, and ships. NOAA has a placeholder in place right now for the P3 for 2021. And there's also a move to get an OS research vessel operating in this area where the uplift is occurring in 2021. Oops, sorry. So in detail, what we would do is we would find these warm fronts, these warm conveyor belts in cyclonic systems. We would characterize the air mass before uplift. We would fly downwind of the systems and characterize the air mass very thoroughly after uplift. And the difference between those statistical characteristics of the air mass in terms of its chemical statistics tells you the effect that the system has had on the air being transported. We would then compare it very systematically with several different models and evaluate which models are getting it right, why, where they're getting it wrong, and what the causes are. Do they have the wrong inputs to the weather system here, which suggests the problems with emissions and processing before lifting? Or are they getting it wrong between the lift, before and after the lifting, which would suggest that they're getting the removal and the cloud processes incorrect. The idea is to do this very systematically, and in many cases, 10 or 12 cases, to build statistics and really test the models in a range of situations, meteorological situations. So the leadership team for this proposal is myself, Jack, and Tom. We also have Mary Barth at INCAR, Tom Hanesko at NASA, and Paul Winberg at Caltech, and a long suite of instruments that is pretty similar to the ATOM payload, with maybe more of a focus on some of the short-lived pollutants rather than long-lived tracers. And this will be submitted in April, and we'll probably find out 6 or 7 months after that whether it will be funded and whether we'll proceed with the DC-8.